Hello everyone. I am glad today to be part of the SBST workshop. So I am Safa Omri and thanks a lot for giving me this opportunity today to present our research paper, Learning to Rank for Test Case Prioritization. Software applications evolve rapidly because of continuous functionality extensions, changes in requirements, code optimization, and fixes of faults. Moreover, modern software is often composed of components engineered with different programming languages by different internal or external teams. And during this evolution, it is crucial to detect unintentionally injected faults while continuously releasing new features. Therefore, many industries use a continuous integration strategy, a common agile technique in which engineers frequently commit their latest code changes to the mainline code base, and developers commonly need to know that unmodified code has not been affected after such code changes, and regression testing is a crucial technique to ensure that these changes do not introduce new bugs at each CI cycle. However, regression testing could consume around 80% of the overall testing budget and require weeks to run all test suites. For example, Amazon is conducting 136,000 builds per day. Google engineers might wait around 45 minutes to 9 hours to receive testing results. In order to reduce the cost of testing, several techniques have been developed, such as test case minimization, selection, and prioritization techniques. The test case minimization aims to eliminate the redundancy in the test suites or remove obsolete test cases to reduce the size and thus the cost. The test case selection aims at identifying the test cases that execute the changed area of the source code, and the test case prioritization is probably used as an optimization mechanism for ranking tests by their likelihood of revealing failures without eliminating any test case from the test suites. However, existing prioritization techniques require gathering code coverage data or performing static analysis, making such techniques time-intensive and cannot be executed within CI cycles, and limited from a practicality point of view as modern software is often written in different programming languages. Moreover, recent test case prioritization approaches shifted to using historical data about failures and successes of test cases based on the hypothesis that test cases having failed in the past are more likely to fail in the future. Unfortunately, such techniques are based on machine learning techniques which do not allow incremental learning but regularly construct new models from scratch, making them time consuming, leading to potentially outdated models and not well adapted to changes in the execution environment. In order to address these challenges, we propose a new test case prioritization approach in CI. We formulate the test case prioritization problem as an online learn-to-rank model using reinforcement learning techniques, and the following problem formulation for test case prioritization is based on basic learning to rank results from the field of information retrieval and applies reinforcement learning to make the ranking approach adaptive and suitable for our CI context. The figure shows the CI cycle. A developer commits code changes that trigger a CI cycle. The test case planning system generates a prioritized test suite, and a subset of the test cases is executed in the specified order until a timeout is reached. It is usually not possible to execute all available test cases within a CI cycle, and when executing the test cases, some will fail and some will not. We investigated two research questions: how efficiently can our approach perform priority-based test selection? And second, how effectively can our approach perform test prioritization? The experiment was conducted on 11 projects. The first 10 projects are open source and all data are publicly available, and the last project is an industrial project. For the first research question, how efficiently can our approach perform priority-based test selection? Our approach learns priority ranks for all test cases, and when applied in the CI context, it might terminate before all test cases are executed. So this behavior is similar to the behavior of test selection techniques, and we use the following standard commonly used metrics in software test selection to assess the effectiveness of our approach when not all test cases are executed. We use the metric test recall. Intuitively, the test recall approximates the empirical probability of a particular test selection strategy catching an individual failure. We compare our approach against 3 test case prioritization methods. The L-Baum's approach, we were able to re-implement the approach since a detailed algorithm is available. With RITEX, the first online learning approach to the best of our knowledge using reinforcement learning in the context of test prioritization and selection in continuous integration. And we use random test case prioritization as a baseline method. It shows that 95% of the test failures are still reported back to the software engineers, while only 40% of the total available test cases being executed, compared to at least 67% of the total available test cases using RITEX. To answer the second research question, how effectively can our approach perform test prioritization? We use the commonly used indicators to measure the effectiveness of test case prioritization techniques. The average percentage of faults detected, the APFD, and the normalized average percentage of faults detected, the NAPFD. The APFD measures the quality by ranking the fault detecting test cases in the order of test execution, and the NAPFD is an extension of APFD to include the ratio of detected to detectable faults within the test suite and is therefore suitable for test case selection where not all test cases are executed and faults may remain undetected. Our approach outperforms almost all studied approaches. We highlighted the best values in bold. Among all the studied projects, the random method has the worst performance. The IOF, Arwal, Druid, and Setxing approaches had the worst performance. To understand this behavior, we analyze the failure detected over the cycles. In those systems, we verify peaks in the failure detection in a few comments and long periods without failures. Moreover, Druid projects had the lowest number of TI cycles among the systems evaluated, and the Setxing had the lowest number of failures reported. In conclusion, we developed a novel lightweight method for test case prioritization in CI based on foundational results of learning to rank from the field of information retrieval using reinforcement learning techniques. Our approach is adaptive and learns ranks from the available test cases during its runtime by observing test results and its own actions and their effects. Our experimental evaluation results show fast learning and adaptation of our approach on 4 industrial case studies. Our method is language agnostic and does not require access to source code and hence can be integrated as an extension or plug-in for existing CI environments like Circle CI/CD, GitHub CI/CD, GitHub Actions, etc. As future work, we plan to add additional metadata to our approach with the hope to enhance its overall performance. Further work should also consider coverage metrics of test cases during the early stage of development when little failure historical data is available. This could allow improving the effectiveness of our approach. In a CI environment, the actual tasks still be solved in each cycle are often similar to previous cycles. Thus, future work on reusing the previous CI cycle results should allow for potential speed ups in future cycles, and furthermore, adding information from the execution environments to the reinforcement learning environment can enhance the quality of the test ranks. This brings me to the end of my presentation. Thanks a lot for your attention.